Welcome to an overview of economics modeling, brought to you by the CGIAR, Foresight and Metrics Initiative. The CGIAR initiative on foresight looks to provide evidence and capacity to help inform complex choices that will shape the future of food, land, and water systems. Supporting this goal relies on the use of evidence to help understand the scope and scale of challenges that confront food systems around the world now, and the likely impact of those challenges in the future. Evidence is also needed to analyze the potential that policy and investment can have in addressing those challenges. Working with partners around the globe, the initiative aims to encourage and grow the community of people and institutions, building and using analytical tools for purposeful, evidence-based research that guides important decisions for the future. Over the next approximately 45 minutes, we will discuss the following. We will start with a discussion on models. What are models? What are their components? Next, we will discuss different types of economic models and go into more detail on partial equilibrium and economy-wide models. We will also discuss the uses and limitations of economic models as well as provide some examples of applied economic models. We will conclude with a discussion of the different uses of economic models and an overview of our online economic modeling course. The team responsible for developing this training and the online course include Mr. Rob Davies, Dr. Karen Therfelder, Dr. Sherman Robinson, Mr. Dirk van Seventer, Dr. Alyssa McCluskey, and Mr. Sherman Gabriel. Making sense of the complex world we live in is difficult. Reality is filled with complex interactions that often don't explain themselves. Understanding the causes, effects, and size of how and why things work, and how we could change them, needs a simplification of reality. This is where models come in. Models are a representation of reality and the connections between different parts of reality. We use them to define how things are, analyze how they behave, and explain a bit about the world. We use them to visualize what the future could look like, identify opportunities to improve a current reality, manage risks, and chart a way forward. There are many different analytical tools for evidence-based research. We use empirical simulation models to analyze the economy. Before we can do that, though, we need to organize our thinking about how the economy works. Economic models aim to define the relationships that exist between different actors. At their most basic level, a market exists where a buyer and seller agree to exchange goods and services using an acceptable medium of exchange, like money. These buyers and sellers are the participants of the economy and can exchange a range of goods and services. For example, producers sell to households, government, enterprises, the rest of the world, and to other producers. The remuneration for this is normally called sales. Similarly, households exchange their labor for wages and salaries, transfer to other households, give government money, in the form of taxes and social contributions, and to firms in the form of savings. As we map out these interactions, we can begin to think how relationships and interactions between different participants in the economy flow. We continue this mapping until all the relationships which interest us are covered. Each of these pathways behave differently. For example, how much households spend is influenced by a range of factors, including their income and the price of the good being traded. In addition to these connections, modelers try to capture these behavioral traits of economic actors in their models. In economics, the relationships are often illustrated in a circuit diagram summarizing the general movement of goods and services. This is known as the circular flow model, and, yes, it is a qualitative model of how an economy works. Another representation of the economy is a social accounting matrix, which summarizes the quantitative value of the goods being exchanged between different participants in the economy. More on this a little later. The task of economists is not to build one model to answer every question we might put to it. Rather, it is to find a model, or set of models, that clarifies the issue they are examining. In this sense, models are like maps. Each map is useful for the domain for which it was drawn. A map drawn for one domain may not be useful for another, even though it is a correct depiction of its own domain. For example, a map for South Africa may be correct but not very useful to find a street address in Pretoria and the other way around. Even in the computerized world of Google Maps, which aims to contain every detail of the spatial world in a single map, we focus on only some aspect of the map when we use it. If we are trying to see where Nairobi is in relation to Kigali, we zoom out, hiding a lot of detail. If we want to get from the Serena Hotel to the Nairobi City Market, we zoom in, ignoring most of the world. As with maps, so it is with models. Models are constructed with a particular domain or application in mind. They can be useful when applied to that domain and unhelpful, maybe even dangerous, when used for the wrong domain or purpose. The domain of a model is multidimensional. It includes its intended use and its empirical base. So economists use many models of different shapes and sizes. In the next slides, Oliver will take you through the general contents of a model and different types of models.
For our discussion that follows, it is useful to have a broad notion of the content of models we focus on. The main elements of economic models are variables, which represent the main entities in which we are interested, such as prices, quantities and incomes, and equations, which show how the variables interact with each other. Variables can be endogenous or exogenous. Endogenous variables have values determined by the model. They are the real objects of interest in our model. The values of exogenous variables are set by the modeler, and change only when the modeler changes them. They may be similar objects to the endogenous variables, such as prices, quantities, etc., but their values are unaffected by what goes on inside the model. An important aspect of modeling is that we, the modelers, cannot change the values of endogenous variables. So, if we want to simulate a particular policy, we have to make sure that the policy instrument we intend to use is an exogenous variable. A particular variable might be exogenous in one model and endogenous in another. Indeed, a given model might treat a variable as endogenous in one application and exogenous in another. The model equations specify how variables relate to each other. Thus, we might have inputs and outputs brought together in a production function. The equations will include parameters, which control the interaction of the variables more precisely. Thus, we might include, in our production function, a total factor productivity parameter, and parameters specifying the elasticity of substitution between inputs. The parameters included depend on the functional forms used to represent behavior, for example, Cobb-Douglas versus CES. Apart from equations that determine the behavior of variables, an important set of equations specify conditions for which the model is solved. Typically, these are equilibrium conditions. The supply of a good equals its demand, or, in macroeconomics, aggregate savings equals aggregate investment. Equations can also impose constraints on variables. For example, we may model a skills shortage by limiting the total quantity of skilled labor available. Solving the model entails using the equations to find values of the endogenous variables which are consistent with given values of the exogenous variables and parameters. These are often referred to as equilibrium values. Solving can often be a complicated process, requiring specialized software and solution algorithms. Fortunately for us, experts have developed a wide range of such algorithms, so solving models is a much easier process now than it used to be. Typically, models are used by first solving the model using the base values of the exogenous variables. Next, we may change the value of an exogenous variable. We call this shocking the model. The shocked variable might be related to policy, a tax rate for example. But it could equally be a non-policy exogenous variable, such as the world price of an export good, or the world price of imported petroleum. We then let the model find new values of endogenous variables, consistent with the shocked, exogenous variables. We then compare these new endogenous values with their values before the shock. Since the only change in the model is the value of the exogenous variable, we can ascribe any difference between the pre- and post-shock endogenous variables to the shock. Analyzing this outcome helps us understand the impact of the shock. We can, of course, introduce multiple shocks, a tax increase, and a rise in world oil prices. But we get better understanding when we change one thing before looking to see how they might interact. In the next slides, Millie will discuss the different types of models. Let's spend a few minutes discussing the various types of economic models. There are many ways in which we can classify models. Some models are constructed in order to help us explore theoretical aspects of the problem. Typically, these models are small, and the equations in them can be solved analytically. The models we will develop are empirical or numerical. Often such models are large, and we use computer-assisted numerical methods to solve them. A key distinction is between models that are used for forecasting and those that are used for simulations and scenario building. Many people, particularly, but not only, outside economics, seem to think that economic models are only used for forecasting. The kinds of models we are interested in here are not used for forecasting. Rather, they are used to construct a controlled environment in which a particular shock can be simulated and examined. In simulation models, we ask, what will this economy look like after this shock to only this variable has worked its way through the economy? In forecasting models, we ask, what will the economy look like if all variables change in the way they are expected to? Need a new correlation, but even models that are constructed to help understand some phenomenon should be tested by seeing whether they make a correct prediction. This might be true, but prediction is not the same as forecasts. When forecasting, in a sense, we make it conditional in that we ignore that there may be some massive exogenous shock that throws the economy off its normal path. In simulation models, we cover in the course a structural model which incorporates detailed behavior and causal links in them. Generally, forecasting models are reduced form with much weaker causal connections. Some other aspects to categorize models include whether the model is looking at one aspect of the economy, which we call a partial equilibrium model, or if the model is looking at the economy as a whole, which we call an economy-wide, or general equilibrium, model. For example, consider a general equilibrium model of raising a tariff on clothing imports. This will likely stimulate output in the clothing sector. That might require additional workers, who might be drawn from other sectors of the economy, reducing output or raising costs there. The reduction in imports might strengthen the exchange rate. Consumers will pay more for clothing, reducing demand. The higher tariff might generate more income for government, affecting the budget deficit and interest rates. This will also affect imports of other goods, not just clothing. Some of these ripple effects might even feed back onto the clothing sector itself. Using partial equilibrium analysis, we might focus on change in the output of the clothing sector, ignoring the myriad of possible spillover and feedback effects. We make the common assumption of ceteris paribus, other things equal. We exclude them from our analysis because they are likely to be too small to affect our impact analysis. We will discuss these model types more in a minute. Models can also be distinguished as to whether they are static or dynamic. There are many ways in which this distinction can be made. Broadly speaking, dynamic models have a time dimension. They are recursive dynamic, so the investment last period updates the capital stock in the current period. They are not forward-looking dynamic models. To have forward-looking dynamics, it requires a smaller model. There is not as much structural detail of the economy. Static models do not have a time dimension. The solution of a static model depends only on values in a given period. The interest is in the two endpoints, the start and the finish, with no attention being paid to the path by which the economy moved from one to the other. In a dynamic model, it depends on past or future values. For a long time, economic methods were dominated by statics. The method of Alfred Marshall was comparative statics. Set up a model, shock it, and compare the solution after everything has worked itself out. Lastly, spatial domain can also be used to categorize models. There are different spatial resolutions from global scale to sub-country, river basin, agroecological zones, national, etc. While all of these model types can contribute to policy analysis, our course will focus on partial and economy-wide, or general equilibrium, frameworks that are single-country, multi-sectoral, calibrated, meaning, benchmarked, static and used for simulation. In the next section, Millie will discuss partial equilibrium models.
We'll now spend some time discussing the partial equilibrium models. First, we will look at how these type of models work and where they are used. Partial equilibrium models tend to analyze supply and demand of one commodity market at a time. This is useful in evaluating sector-specific questions, where spillovers to other parts of the economy are less important. The narrower focus on a sector makes partial models more straightforward to build, run, and modify. This does not necessarily mean that with the simplification comes high detailed specifications. Multi-market partial models, which look at a collection of different commodity markets, but not necessarily an exhaustive set representing the whole economy, allows simultaneous analysis of the functioning of multiple commodity markets, often within the same sector, or a closely related group of industries. Although they analyze multiple markets, they may not necessarily interact with each other in the same framework. Multi-market models offer a detailed view of commodities in a specific sector, which other models might treat in a more aggregated way. We can avoid making assumptions about a larger sector which has distinctly different segments. For example, many general equilibrium models offer limited detail about the agricultural sector which, in reality, comprises a variety of field food crops, horticultural commodities, livestock, and other feedstock. It is sometimes data-intensive or computationally inconvenient to include this disaggregation in models where it is not necessary to view agriculture in extensive detail. Multi-market models have fewer data requirements, especially compared with larger, general equilibrium models. Data needs vary, however, based on the number of commodities analyzed and the complexity by which supply and demand are determined. Despite a detailed view of specific commodities, multi-market models are smaller than general equilibrium models as they represent a specific part of the economy. Modeling is easier to describe and implement, and results are easier to explain, but this can be a flawed assumption because of their focus on a limited set of commodity markets. Multi-market models are typically weak in describing the trade-offs and feedback loops that occur in the broader economy. This can sometimes miss important secondary effects of a policy or investment. Also, there is generally no consideration of the impact on macroeconomic balances. The kind of data required for a partial equilibrium model largely depends on the variables and parameters specified in the model. In a model looking at agricultural commodity markets, for example, datasets that include annual time series of production, demand, trade, prices, tariffs and subsidies, and other macroeconomic data. These are often taken from a variety of national and global data sources, including the databases of international organizations, national statistical agencies, survey data, literature, and expert consultation. There are several multi-market models focused on the agricultural sector. These include IFPRI's impact model, the IGLINK-COSIMO model, managed by the OECD and FAO, the MAGPIE model, led by the Land Use Group at the Potsdam Institute for Climate Impact Research, and the Globium model by YASA. Many of these models are, at their core, economic partial equilibrium models, but many also link to other models, sometimes embedded within the modeling framework. We've listed some examples here of grid-based crop models that offer spatially distinct outputs on yields of different crops and some examples of water models. This slide is a placeholder for an example of an applied partial equilibrium model. What type of questions and exercises can we explore with these partial equilibrium models we've discussed? Here are some examples. What is the impact on global trade and world prices of agricultural commodities due to changes in production due to climatic effects and extreme weather? Simulations of investments on production and prices. Simulations of risks to food security and hunger. Comparison of alternative social and climatic pathways. In the next section, Oliver will discuss economy-wide models.
While we just discussed partial equilibrium models that tend to analyze supply and demand of one commodity market at a time, we'll now move on to economy-wide modeling that can be conducted at the macro and at the multi-sector, or meso, level. Both macro and multi-sector economy-wide models are concerned with indirect, or feedback effects. We need to discuss what we mean by an economy-wide modeling framework and why we want to use it. We want to model the economy as a whole, but at a disaggregated, or meso, level, because we believe that economic structure matters. By economic structure, we think about industry structure, which sectors are important and what are the linkages between them. We think of labor markets and how they connect to the industries and the various types of households through the distribution of income. However, macroeconomic constraints are important considerations. The results of our economic modeling need to add up in the context of the economy's national accounts. That is why the latter is used as the benchmark. Why should policymakers be concerned with the whole economy using an economy-wide framework? Well, while direct effects on target industries, using partial equilibrium analysis, are often quite obvious, indirect effects could still be significant from a policy perspective but generally less obvious. There may be unintended impacts in addition to the intended impacts. This may be of interest to the political economy of interest groups. Returning to the example we discussed previously regarding higher tariffs on clothing. This may benefit workers and enterprises in the clothing industry, but a typical indirect effect is an increase in the domestic import price of clothing. This may have a negative impact on lower-income households who spend a higher than average proportion of their budgets on these items. While workers and enterprises may be able to lobby for the higher tariffs, it is not clear who may have the interest of low-income households at heart. Policymakers would therefore like to consider winners as well as losers, possibly with the aim of somehow compensating the losers through one or other redistribution measure. It is those indirect effects that require a disaggregated economy-wide framework. Economy-wide modeling uses data from a range of sources. Another major benefit of taking an economy-wide approach is that it forces us to check the data for consistency. In that way, it shows where there are gaps in the data and indeed in our knowledge. Moreover, as mentioned earlier, the adding up of modeling results forces a reality check on the plausibility of economic policies other than related to data. Often the effects of policies are seen, particularly by policymakers, as adding to whatever is already going on. A large infrastructure investment project will, we are told, add to total investment in the economy. In practice, they may divert away from, or substitute for, current activity. If the supply of cement is limited, the large project will have a negative impact on other investment projects. The net effect on investment may actually be limited. Economy-wide thinking is needed to pick up these important substitution effects. In summary, plausibility is important. We cannot make changes to economy that break resource constraints. The system of national accounts as a common benchmark is useful in this regard. While there is much concern about the veracity of the system of national accounts, its greatest contribution still is that it makes all participants to the economic policy debate sing off the same song sheet, if you like. In that way, unnecessary discussion about different data sources used in the debate are avoided or at least reduced. In conclusion, we argue that economy-wide modeling results in better economic thinking. Economy-wide policy analysis and modeling can be considered as consisting of three broad categories. 1. Macroeconomic and dynamic stochastic general equilibrium, or DSGE models. 2. Linear multi-sector models. And 3. Computer general equilibrium, or CGE. On macroeconomic models and DSGE, usually their structure is limited. Often this is because they are more interested in macro outcomes rather than at a more disaggregated level. But it is also because they are often econometrically estimated and the data will not support estimation of disaggregated models, particularly in less developed economies, or LCDs. These models focus more on financial variables like inflation and interest rates. Linear multi-sector economic models offer more detail, in particular in terms of economic structure and linkages. But the behavior that is assumed is linear, or very simple. They can be set up in Excel. Some examples in this method category include input-output and supply-use models, which model the interactions amongst industries and commodities, social accounting matrices, or SAM for short, look at adding factors, income distribution, and commodities, and the models based on them are often referred to as multiplier models, and are useful for rapid deployment, where shocks are relatively small. The impact of a shock typically moves in one direction. If the shock is positive, the impact will be positive, or the other way around. Then there are CGE models. Based on the same detail as the linear models mentioned previously, their behavioral responses are more sophisticated, based on standard neoclassical or other economic theory. While they contain similar linkages that we see in the linear multi-sector economic models, CGE models become more complex, looking into behavioral responses and more meaningful economic theory. Specialized software is required to solve these kinds of models. We will cover both the linear multi-sector economic models and CGE models in our course, but we will not review macro or DSGE models. Next, Channing Arndt will discuss an example of a CGE model used to evaluate the impacts of COVID-19 lockdown on income distribution and food security in South Africa.
Hello, my name is Channing Arndt, and I'm pleased to be able to speak with you today about some analysis that we did in South Africa on COVID-19 lockdowns, income distribution, and food security, and analysis for South Africa. This analysis was published in Global Food Security in September 2020. This was an interesting analysis in that it is exactly what was presented to the government of South Africa. I remember well, I walked out of the office on March 13th, 2020, and I didn't go back for months. What I did get was a phone call and a couple of mails from the head of economic policy from the National Treasury of South Africa asking if we would please look at the implications of the lockdown policies that they were about to deploy. And over the coming weeks, we were finished by early April. We did a simple analysis that looked at what are the direct implications of the lockdown. So we went and looked at which sectors where workers were going home and therefore wouldn't be able to produce. And we concluded that a very simple approach would work well. It's called a SAM multiplier approach, which you'll learn about in sciences. SAM multiplier approach, we can impose these direct effects of the lockdown. And what the SAM multiplier approach will do will be to get what we call the multiplier effects, because if we take away demand, for example, from a particular sector, that is in fact taking away the income of that sector or the people who work in that sector, which then in turn influences their demand. And what we end up finding is shown in this particular graph that looks by broad industry. And the impacts, the yellow is the direct effects of the lockdown. These are what was shut down, so construction was strongly shut down. And the green are the indirect effects. And you can see that the overall, which is the bar on the far right, the total, the indirect effects are larger than the direct effects, and the effects are very, very large. So in South Africa, the flow value of GDP kind of, you could think of it as a river of goods and services, was reduced by 34% at the maximum point in the lockdown, according to this analysis. And that actually turned up quite well when we looked at what actually happened with the benefit of hindsight in terms of production values, for example, in mining and in electricity, are surprisingly close to the estimates that we got from the SAM multiplier analysis. So as a consequence of this, we were able to really raise the warning that these lockdowns were in fact a real threat to food security to people who were living on the edge. If they didn't have savings or other sources of income, as most people who are close to being food secure do not, their loss of income, which was substantial, led them to be unable to actually purchase the food that they need. And this underpins some of the expanded social protection policies that the government of South Africa actually deployed during the lockdown. So thank you for this opportunity to speak to you today, and I wish you well in your course.
Now that we have an understanding of the different types of economy-wide models, let's be clear about what these models can and cannot do. An important question is what economy-wide model can and can't do. As with all horses for courses, these models are not useful for some questions. Since they are not micro-models, they do not show how a firm responds to an intervention such as carbon tax. In fact, it's the other way around. This information could be collected from enterprise interviews and surveys, or micro-enterprise level modeling analysis, which then has to be supplied to the economy-wide models. Once that is done, we can then look at the economy-wide implications if firms respond in a particular way to an intervention. Although economy-wide models are usually not considered for forecasting, they can help to disaggregate a macro forecast down to industry level. In summary, economy-wide models are useful as a scenario laboratory in that a controlled environment can be created to examine a certain policy intervention in which other conditions, such as a sudden collapse in the world price of the economy's main export commodity, can be ignored. Since economy-wide models offer some industry-level detail, typically a large output of numbers is generated. However, understanding the narrative is often more important than the numerical results. The models help us understand the channels through which policies work. Communicating these causal chains to policymakers needs to be conducted in such a way that they make sense in Econ 101 terms. The models are not black boxes and should not be presented as such. Phrases such as, "This is what the model says," should be avoided when trying to explain the results. Availability of accurate and detailed linkage data is scarce in developing countries, in particular in Africa. But economy-wide models remain useful even if the data is not as accurate as we like, as long as it contributes to the narratives that we mentioned above. Although most economists are not interested, as much of the narrative is based on the data, we have to pay attention to data and its improvement. Next, Faika Hartley, then Shantianan Devarajan, will discuss a couple examples of applied CGE models.
Your research takes a look at the introduction of the biofuels industry in Mozambique. What was the underlying basis for doing this research?
Sure. So at the time, there was a rising interest in using biofuels as a substitute for more traditional fuel use in the transportation sector. And the aim was that to increase biofuel use in order to reduce mitigation in the transport sector. We were specifically interested in looking at using sugarcane for biofuels production because as a crop, it doesn't compete with food demand in the country. So we used the dynamic CGE model to explore the impacts of the development of a new biofuels industry in Mozambique. We the social accounting matrix, which is the underlying database for the model, to include specific information about what a biofuels industry would look like. And this information we got from field studies, and then we also looked at industry studies to try and understand what were some of the potential byproducts that could come from a biofuels production industry. So the results from our study showed that the implementation or development of a biofuel sector in Mozambique would have a positive impact on the economy, on growth as well as on employment. And what we also found is that if you have multiple product chains associated with the industry, such as, for example, electricity production, the impacts on the economy would be much larger. We chose specifically to use the CGE model because we were looking at a new sector that wasn't existing in the economy. And so we wanted to introduce the sector into the economy and try and understand the direct and indirect impacts that the sector would have on other sectors in the economy through linkages, but also the impact that the sector would have on prices, and not only final commodity prices, but also prices of resources, because it's competing for things like land and capital. Using this methodology and this approach allowed us to not only look at the benefits of having a biofuel industry, but it also enabled us to look at the unintended consequences of developing a biofuels industry. Another advantage of using the CGE model is that it combines the production side of the economy with the impact that it can have on households. And so because it was providing us with this consistent framework and simulation laboratory, we could look at the impacts of biofuels production on households from multiple fronts. The two key things that I think would have been important in further understanding the impacts of the development of a biofuels industry in Mozambique. The first was maybe a bit unpacking a bit the potential impact from having an infrastructure or water supply constraint on being able to grow sugarcane and turn that into biofuels. And then the second was being able to look at the impact of the biofuels industry on individual households, specifically vulnerable households.
Hello, I'm Shanta Devarajan, and I'm going to talk about the uses and abuses of CGE models in policy analysis. The first one is about NAFTA, the North American Free Trade Agreement, which was signed in the early 1990s between the US, Mexico, and Canada. And while the treaty was being discussed, there was concern about the impact of such a free trade agreement, especially on the agriculture sector in Mexico. Mexico at that time was undertaking various reforms of the agricultural sector, and there was a concern that these reforms might either be derailed or undermined by a free trade agreement with the United States, and in particular with the effect on many of the corn farmers, or people working in the corn industry in Mexico, which would suffer from increased imports of corn from the United States, which was a lower cost producer. So a CGE model was used to examine the impact of a free trade agreement on the agricultural sectors in both the US and Mexico. And what this model showed was that while the corn sector would suffer, would actually lose competitiveness, the increased possibility of selling high-valued goods such as fruits and vegetables by Mexico to the United States would partially offset that effect. But the other thing that it showed was that this effect would not be immediate because the fruit and vegetable exports was actually at a very low level. And so this gave this analysis, which, by the way, was supplemented by various detailed sectoral analyses. And that's one of the things that we find is that when other models give you similar results, they are much more credible. But what this analysis said was that they may need to modulate the pace at which they do agricultural reform in Mexico, because it'll take a while for the benefits of the free trade agreement to kick in. And that that actually was the basis of the plan. And I think there was an agreement that the relaxation of tariffs and trade would take over 15 years. But now another analysis on the effect of the free trade agreement on in the U.S. Actually had an unfortunate outcome. And that was an analysis that looked at the effect of the NAFTA on unskilled or low-skilled wages in the U.S. And what that analysis, it was a CGE model, what that showed, which was consistent with the Stolper-Samuelson theorem, was that there would be a slight decrease in unskilled wages in the U.S. But because it was showing a decrease, the agency that did the analysis chose not to publish it. But nevertheless, the AFL-CIO found out about it and suddenly started broadcasting that as a result of NAFTA, 60% of American workers would suffer. Now, this created quite a sensation, and the agency that had previously chosen not to publish the study had to publish it and had to show it, because what the study showed was that wages, real wages for unskilled workers would fall by 0.02%. This was almost negligible. It was within the margin of zero effect. So they had to reveal it, and they should have done it in the beginning, because then otherwise it sounded defensive, and it also sounded like they were attacking the AFL-CIO, which was hardly the case.
We have told you why models are important. That is why the Foresight and Metrics Initiative, as part of its mandate to strengthen evidence-based policy, has designed online courses around modeling. Before discussing the course, let's identify the different types of model users the courses are aimed at. There are 3 types of economic model users. First, senior policy managers need to know the policy relevance of the analysis and understand enough to evaluate reports that use these economic models. We can think of them as our informed riders. They hail the taxi and need to make sure that the driver is going in the right direction. The second group of economic model users are our drivers. Regular policy analysts, who are frequently asked to interpret and report on results to their management, and may need to run existing models, using a standard setup. They can, in addition to being an informed driver, drive the car themselves. In other words, they know what the controls do and how to operate them. Our third and final group of economic model users are our mechanics. Modeling specialists, who adapt and develop the model. They can, in addition to being an informed rider and an active driver, go underneath the bonnet and tune the engine. It rarely happens that a CGE model is built from scratch. From an institutional perspective, it is important to build a solid institutional modeling framework. By training all 3 model users in an institution, you create a solid capacity for understanding model results, our informed riders, analysts that can run and interpret models, our drivers, and model specialists that can develop and adapt models, our mechanics. A cohesive training, like the one we will present next, sets a framework for good modeling practices and consistency in model use across the institution that can be sustained over time. Whereas if you train a single individual, the knowledge capacity is limited and may or may not be retained. In the next section, Oliver will discuss the contents of the online course.
In the following section, we will discuss an online course on economic modeling. We will discuss how the course is set up to address the needs of the 3 different groups of economic model users. On behalf of the CGIAR Foresight and Metrics Initiative, an online economic course is currently being developed. The target audience for this course is ministry workers and policy analysts, networks and research institutes, and university students at the master's and doctorate levels. The first module on model basics is targeted at all 3 levels mentioned earlier, meaning senior policy managers, aspiring regular policy analysts, as well as potential modeling specialists. This module is designed as an 8-week, instructor-led, asynchronous, online course with required interaction and multiple live webinars. In this first module, you will learn about the macro and micro economic relationships in partial equilibrium, multi-market models, followed by general equilibrium models, through the exploration of a social accounting matrix, or a SAM. You will also gain an understanding of the requirements for, and sources of, economic and biophysical databases. You will explore a demo model to learn about the elements of an economic model and perform a variety of hands-on exercises. After Module 1, we offer 2 pathways. One pathway will focus on multi-market models. The second pathway will focus on CGE models. These modules are targeted to aspiring regular policy analysts, as well as potential modeling specialists. The first multi-market module provides an in-depth study of a partial equilibrium multi-market model. This includes the economic theory that underlies supply and demand behavior, data inputs and key parameters, and skill development in the critical assessment of multi-market model results. There will be hands-on exercises with a simplified multi-market model. Participants completing this module will have the ability to run a multi-market model and understand and explain the economic behavior that drives experiment results. The second multi-market module provides training in developing analysis using a simple country-level multi-market model in the GAMS modeling platform. This module is targeted at potential modeling specialists. Participants completing this module will build applied skills in defining experiments, evaluating data and parameters, and explaining, critiquing and effectively communicating results. The first module in the CGE learning pathway is CGE Model Setup. This module provides an in-depth study of a computable general equilibrium model, including the economic theory that underlies supply and demand behavior, data inputs and key parameters, skill development in the critical assessment of GGE model results. There will be hands-on exercises with an Excel interfaced CGE model. Participants will complete this module with the ability to run a CGE model and understand and explain the economic behavior that drives experiment results. The second CGE module provides training in developing analysis using a static, single-country CGE model in the GAMS modeling platform. Participants completing this module will build applied skills in defining experiments, evaluating data and parameters, and explaining, critiquing and effectively communicating results. After modules 3A and B, we will bring the cohorts from both learning tracks back together for a virtual conference on economic models. We will review lessons learned, listen to student project presentations, and discuss next steps and future work. Potential future modules to the course may include advanced training in multipliers, the impact model, RIAPA model, building a SAM, and GAMS advanced programming. These advanced courses will be determined based on participant needs discussed throughout the course. For more information on the online course, please contact TBD. We thank you for your time and interest in learning more about economic models. Here are a few references for further learning.